So dear students, in this lecture we will discuss about the introduction of the state variable feedback system and the design procedure which is used to design the controllers using state variable feedback system or state variable feedback theory. This lecture covers introduction to the state feedback design and controllability and observability. Now, what is state feedback or state variable feedback? What is this? So, basically, state variable feedback is, as the name suggests here, state variable feedback. So, that means when we have a system, we have its state as an output. This state is being fed back to the system. So, here you have this. So this is the control signal basically, or UT, if it is time domain. If it is discrete, then it is UK. So what we are doing, we are feeding this state back to the system and adding it with the control variable. UK is nothing but a control variable, right? Now, as the name suggests, that state variable feedback means a variable which we call as state. Now, what is state, that also we will understand. So, state variable feedback is a way, a technique, or a method in which we feed the state variable back to the system so that we can obtain the desired control action. So, as we have already discussed, that the difference between transfer function approach and state space approach is that in transfer function approach, we are more concerned about the input and output, right? So we can write transfer function. So since it is Laplace of output to the Laplace of input with initial conditions to be 0, right? So it deals with the input and output of the system. It deals with the input and output of the system, right? But if we talk about the state variable feedback, in state variable feedback, we deal with the state of the system, right? So state is nothing but the internal information of the system. Okay, state is nothing but it is the internal information of the system, right? So instead of only looking at the output of the system or input of the system, we are now more concerned about the internal dynamics of the system or internal information of the system. Okay, so this is similar to the analogy that if you go to a doctor, so there may be a possibility that doctor would just look at your appearance, just will see your face and observe your voice, and on the basis of that, the doctor could interpret that you are sick, you are ill, or you are not healthy. So this is based on the outer appearance of the patient. However, the second possibility could be that you go to a doctor, the doctor would measure your temperature, the doctor would measure your blood pressure, your heartbeat, your oxygen level, and various other parameters. So, after that, the doctor would come to a conclusion that you are not healthy or you are healthy, whatever, right? So accordingly, the medication or the treatment would be suggested by the doctor. Okay, the state is something like that. It is the internal information of the system. It tells us about the internal dynamics of the system. Okay, now in state variable feedback method, which we use to design the compensator. So there are basically in conventional control theory, we have the techniques such as root locus, border plot, Nyquist, polar plot, route array criteria, and there are a few more conventional techniques which we use to design the compensators. Compensators means the controllers, right? So, but in state space approach, we use the state variable feedback technique to calculate the control action. Now, what do we mean by control action? It is to obtain the controller's output. Now, what is the controller's output? It is UT. So, UT is the control action basically. And this control action is based on some law, it is based on some rule, right? So in this lecture we will discuss a little bit of that particular concept which is related to state feedback control or state feedback controller design. Now, before proceeding to the design of control using state variable feedback approach, we need to know about the two very important concepts which we call as, okay, controllability and observability, right? So what is controllability, what are these, what is a controllability and what is the observability? This is the question. Controllability, so we can like take these two words, control plus ability, observe plus ability. Now here, when we say controllability and observability, we actually mean to say that whether the system which we are dealing with is controllable or observable or not, whether it is a, whether we are able to control that system or not, whether we are able to observe that system or not. Okay, so before designing the controllers or compensators using the state space approach or state variable feedback approach, our first objective is to know whether the system which we are working with, we are dealing with, is controllable and observable or not, right? So now, how to identify, how to know that whether the system is controllable or not, that is the next thing that we will discuss. In state variable feedback approach, what we do is we place the poles of the closed loop system, which are actually the eigenvalues of the system matrix in state variable format. So what is the system matrix is? So system matrix, what is this? So what is the characteristic equation? So these are some questions that would be answered in uh, next lecture or future lectures, right? So now see, the ultimate objective of state variable design is to place the poles precisely on the desired location, and so that we can meet the desired performance specifications. What we need to say, like, we have the complex plane here, j omega, and this is the real axis. So we all know that if poles or zeros are placed here, the system is unstable, right? It is unstable. Now if the poles or zeros are placed here, so system is stable. This is left hand side, this is right hand side of S plane, right? So now by using this state variable feedback design, we actually, what we are actually doing, we are finding or determining the location of the poles in such a way that we can get the desired location. So the objective is to find out those desired location of the poles. Poles of what? Which poles? Which poles? Okay, so these are the roots of the, or you can say eigenvalues of the system matrix, right? So this is the design objective. Now to achieve this design objective, we need to know whether our system is controllable and observable or not. Let us come to the controllability and observability. Basically, the concept of controllability was and observability was introduced by Kalman in 1960. Controllability and observability play a very important role in design of control systems in state space. Means if we want to design control system, uh, control system using state space approach, controllability and observability play important role. They play important role. Now, what are the conditions for the system to be controllable? Sorry, what is the condition for the system to be controllable? What is the system for, what is the condition for the system to be observable? That will be discussed. However, the controllability and observability of any system would help in determining the complete solution of the control system design problem. Okay, if our system which we are dealing with is not controllable or it is not observable, then we are unable to find the solution of the problem, right? So this is how, that is why the controllability and observability are very important. Now, what is controllability? Now, let us come to here. What is controllability? Controllability is basically defined by the definition, the standard definition, which says that any system is completely controllable if there exists an unconstrained control signal, unconstrained UT. UT is nothing but the control signal, means the output of the compensator. So unconstrained means uh, not bounded. There is no boundation, right? There is no boundation on the control signal. So now Any system is completely controllable if there exists an unconstrained control that can transfer any initial state of the system. Now, this is the initial state. It could be zero, it could not be zero, right? To any other state or to any other desired value of the state, basically, in the finite time. This, for example, you have a system whose state is which is a system with state vector xt. So at, let us say, time t, it is, or t0, it is here. T0 is not always mean that it is at the origin. No, t0 is, let us say, here. So if your control variable is able to take this system state from the value xt0 to a new value xt in some finite time, in some finite time. So we would say that the given system is controllable if this control law is capable of transferring all the states of the system from its initial value to some final value within the finite time, stipulated time, specified time. Then we would say that the system is completely controllable. It is completely controllable. Right. So now, how will we identify whether the given system is completely controllable or not? For this, we will take a system which is x dot t is equal to axt plus but. This is the state equation. Okay, this is the state equation. Right. Now, we can examine the controllability of the system if the controllability matrix of the system has full rank, means it is equal to n. Now what is n? N is the order of the system, right? It also indicates the uh, states of the system, states of the system, right? So the rank of the controllability matrix should be full. Now full rank means it should be equal to n. Now what is n? N is the number of states or order of the system. For any single input, single output system, so this is for CISO. CISO is single input and single output. So for MIMO systems, n will remain same as this is the case of state space. We all know. Okay, so B would be n into m. So this is like the matrix is the dimension of the matrix will increase. So the controllability matrix is given by PC, which is this, that is B A B A square B dot 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 A n minus 1 B, where PC, which is the controllability matrix, is a n by n matrix. So its dimension is similar to that of A, similar to A. A is also n by n matrix, right? So how will we identify whether the system is controllable or not controllable? Just by knowing the controllability matrix. Okay, so the condition is, the requirement is that the determinant of PC should be non-zero. If the determinant of PC is zero, the system is not controllable. So we'll write here, in other words, in other words, if the determinant of PC is equal to zero, then the system is not controllable, right? So this was about controllability. Now let us come to the observability. So observability, observable, whether sorry, whether the given system is observable or not. Now, what does it mean? What does it mean? It means that observability here is something which is associated with the state of the system. So, observability is associated with the state of the system, right? It is associated with the state of the system. What is that thing which has to be observable? It is the state of the system. The state of the system should be observable. So what we will say, we will define that the system is completely observable if and only if there exists a finite time. So there we were talking controllability, we were talking about the control law. Here we are talking about the finite time. So how will we define this observability? A system is observable if and only if there exists a finite time such that the initial state x0 can be determined from the observation history yt given the control law ut. That means you have a system whose output is some state and input is the dynamics, and you have a control signal ut coming here, and then state feedback. This is the even this is the feedback, right? Now now if this control law is sufficient, if the control law ut is sufficient in observing, sufficient along with the initial conditions, okay, sufficient along with the initial information of the system, then system in the finite time, the system is said to be observable. And if your control law along with the initial state, so the crux here is that you should have control law and there should be some initial state which is known to you, right? If these two conditions meet and these are sufficient to know the state of the system, to observe the state of the system, we will say that the given system is observable, right? So let us consider a system which is represented by the state equation. This is the state equation and this is the output equation. Now where A is the state matrix, C is the output matrix, and like that. So if this is the case, this is the system, so we can examine the observability by determining the observability matrix, and the rank of this observability matrix should be full, that is n, where n is the order of the system or states of the system. For example, for example, if a system is of second order, then n is equal to 2, right? So that means the system has two states, right? So the observability matrix is given by CA square dot 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 CAN minus 1 transpose. So it is something like this. So we can write the observability matrix, which can be written because it is a transpose here. So it could be written as like this. So P naught is equal to CA dot 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 CAN minus 1. So its rank should be equal to full n. So how will you find out rank full? If determinant of this matrix is not equal to 0, then P node has full rank. Else, okay, not else here. So we'll write here that, so okay, so uh, the observability matrix is equal to CA dot 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 CAN minus 1. Its rank should be n. So we can say determinant of P naught should not be equal to 0. So if so, the system is observable, else not observable. So basically, if our systems are not observable, neither observable nor controllable, so it is very difficult to design controller, almost impossible to design controller for such system. Though we have some advanced techniques which could be used to, design compensators for such kind of systems, but they need a lot of information and time to do so. So this was about controllability and observability. In our next lecture, we will study the pole placement design technique. Thank you so much, guys.